Today I want to talk about two concepts that I think are super important: autonomy and asynchrony. These two concepts play a very, very important role if you want reliable systems. So a little bit about me. I've been a software nerd for over 15 years. Back in my very youthful days, I used to believe calm is love. And I used to think that web services and SOAP made the world go round. But that was back in my very, very youthful days of development. But during the years, I've learned. And the past about 6 or 7 years ago, I started to do more stuff with event-driven architecture and event-driven programming. And that kind of opened up a whole new world. I found that if you build a system where all your components are expressing itself as events and messages, you're able to build a and loosely coupled system. So this was my aha moment, back about 7 years ago. And I was able to use that knowledge and build some systems. And today I work for Particular Software. Particular Software makes N-Service Bus. Does anyone here know or used? Oh, a few. So N-Service Bus is a reliable messaging platform which helps you build, use event-driven architecture in your systems. So first, let's talk about autonomy. What is autonomy? In the most bare minimal of things, it's the ability to do something without being reliant or dependent on another, right? This is Steph Davies, and she's climbing Scarface, solo climbing, so without the aid of any rope. It's scary. I can assure you building autonomous services is not as scary as that. But oftentimes we have components, and these components either need data or they need another component or service to process something first before it can continue or resume its operation. So we have a lot of stuff like that to deal with. This is the last picture that Cassini transmitted before it delved into the depths of Saturn. Think about like rocket science. I mean, what we build today may not be rocket science, but think about like the autonomous how systems need to have been autonomous in order to achieve something like this. You can't have a command control style of architecture. You can't expect something from the command center in Earth to relay a command to Cassini and wait for it to happen. That's just not possible. These systems that we write need to be able to be autonomous and be independent. And if something were to go wrong, take compensating actions so that they can move forward and be more reliable. So let's take our own human brain, for instance. We have about 1 billion nerve cells, like communicating with each other. And there's this fascinating TED Talk. It's called 3 Clues to Understanding Your Brain. It's super, when I first watched it, after I watched it, I had this aha moment. I was like, wow, our brain has like beautiful bounded context, and it's so beautiful and autonomous. It's because, I mean, if something were to happen to one function, let's say, you poked your eye or something happened to your eye, that doesn't mean you lose the ability to hear. Those are two different things, but they're able to be autonomous, and you have functionality. Just because one thing goes down doesn't mean the entire system is down. Every other part of the system is able to work independently. So I urge you to watch that TED Talk. You can Google TED Talk and phantom limb to get to the link. This neurologist, he found a really, really cool way of how to treat patients who had the phantom limb syndrome, who were experiencing excruciating pain after amputation. And it's very clever. And after watching that, I can assure you, you will be with me thinking like, woo, bounded context for the win, and autonomous and asynchronous for the win. So how do we take this and then translate to what we have? Asynchrony is also a very important part. We need to be able to do things together at the same time. So if you relate this to our own human experiences, and let's take child development. When a child is growing, there's a lot of things that's happening. There's physical growth, and there's emotional growth. During those early years, the child is absorbing so many things and forming a lot of patterns and learning that's occurring. So in this stage, you can't expect like one thing to happen first before the next part to happen. They need to happen at the same time. So asynchrony is a very, very important part. So if we take this real life stuff and then kind of like translate to what we see in code, sometimes we have code like this. This is an example from the Microsoft, one of the doc samples for WCF service. So at the onset, it's pretty simple. You have a calculator service, and that you pass it some parameters, and you expect an outcome. So can anyone tell me any design flaws with these 3 lines of code, or 4 lines, or more, if you have the comments? Yeah. We have to wait to. Right, so there is some waiting involved. So if you really look at this code assumes certain things. First is the add method, right? This could be a web service or some service running in Cassini. But the code here assumes that you make that call, you get that result, and the flow continues. But what if the result isn't coming back to you instantaneously, right? There could be a delay depending on where your service is running. So there is inherently latency involved, but those lines of code, hide those. You're not taking into account the latency. What if the call doesn't come back? Well, the operation could end up in a timeout exception. Now, when you get timeout exceptions, they don't tell you much other than timeout has occurred. The operation, this add operation that's happening in the service, could have completed successfully on the server side. However, the client timed out. So how do you deal with that? And just because the client timed out, now can you retry this operation safely? So if you retry, is it one of those payment systems where you charge the client every time? So you can't really retry. You're going to be charging the person, your customer is not going to be very happy. Your company might make a lot of money with the retries, but you're going to have some angry customer calling you. So you have to think about latency. The other thing is, it also assumes that the network is reliable. This is a fundamental fallacy in distributed computing. We assume that the network is reliable. Now, how many of you here have had to deal with some outage in their network at one time or the other? Yes, right. But we don't think about this when we're actually writing the code. We all know that the network is not reliable. We used to have this term, we have to IT-proof our code. So the IT-proof stuff comes in because you assume that the network that you work isn't reliable. So here, retries can help with like the transient things. Like if the network is like down for, it could be just a momentary glitch, in which case retries here work beautifully. The next time you retry, it would be fine. But again, it depends on the type of operation that you're trying to do, if that's safe to retry or not. And again, those are the things that you need to take into account when you consider this code. It's again, these things are hidden. They seem very simple. It's 3 lines of code or 4 lines of code. But they hide these design flaws or design things that you need to be aware of. Because if you think about those, then you will build retries in your code. You will think about what type of compensating action do you take if you expect that call itself to be taking lots of time. Oftentimes, we build services. We mock out services because we can't really test production stuff with the third-party stuff. So we could have this local thing running in our machines just to test everything else. And everything else will work beautifully because this thing is part of your network and it's running in one of your servers. But when you translate that to the actual real thing that's running, a service running far, far away, then you start all of a sudden seeing these timeout exceptions happen. So thinking about these two things, like latency and network reliability, will help you think about your design in a different way. So what prevents you from writing autonomous code or asynchronous code? Inherently coupling. So coupling, in the simplest of terms, it's just like a degree of measure, if you think about it that way, of how many dependencies you have. So let's say you have a component. And if you want to change that component, think about how many other components are going to be impacted by that change. So you could, if you want, like have fancy metrics, you could have some sort of a measure and do some impact analysis. Like if I make this change here, how is it going to ripple against all these other components? But one of the main culprits is temporal coupling. To kind of understand temporal coupling, I want you guys to imagine this. Okay, you want your coffee. You're trying to get started. You're trying to get started your day, and you crave this double espresso macchiato. So you're going to Starbucks, and then the line is like insanely long. It's crazy long, and it's taking a large amount of time. And you wait patiently, and finally you get to the cashier. And this is what happens. So the cashier gets your double espresso macchiato order. And then he walks over to the barista and says, hey, here is the order, and you make it. The barista has to do what, steam the milk, make the espresso. All this while, the cashier is just looking at the barista, standing there, right? And then the barista makes the coffee, hands over to the cashier walks back to you and gives you your coffee. Well, I don't know about you, but if this were to happen to me, I'm going to be mad. Right? So if we take this sort of thing and translate to the actual software that we're writing, this is kind of how it really is. You have two services. You have the cashier service and you have the barista service. The cashier service, when it gets the order drink, goes and makes this call to the barista and then waits until the barista comes back and then does what a cashier is actually supposed to do, which is process your card, right? The one thing that the cashier is supposed to do, take your card, make that transaction, give the card back to you, does that, and then returns the drink. So temporal, think of temporal as something that's dealing in time. And coupling, as you know, in software is bad. So anywhere where you have these two services that are coupled in time, where you have one service that cannot complete its operation because it's waiting on the other service to do whatever it is it's doing, then you have temporal coupling. So this is really one thing that will prevent your systems from being autonomous and being able to do what it really is supposed to do. So how do we solve this problem? Well, again, Starbucks to the rescue. Well, if you think about what really happens in Starbucks, you go, you walk in, the cashier takes your order and writes it in a cup, like your double espresso macchiato, however you want it, upside down, all the different, Starbucksy things, right? They write it down and they leave it on a queue for the barista, and they charge the money, and then the cashier's done with you. you're done. And this cup gets queued for the barista. Now, you're free to do whatever it is. You check your Slack, respond to very important emails, try to yell at your son for not having turned in your grade. All the things that your normal life goes on, you do those things. And the barista picks up the cup and prepares the drink. And when the drink is done, he says, hey, Indu ready, coffee's ready for Indu, right? And so you just go and pick up your coffee, and life is great. So again, and that will make everybody happy, right? Life is good. So if we were to translate this, again, into software services and code, we would achieve this by using messaging, kind of like what happened in Starbucks. So we use a pattern called publish subscribe. And publish subscribe is just one of the 100+ patterns that are described in the Enterprise Integrations Pattern book, which is really, it's one of those old gems. So there's so many patterns there that you can use to translate like real life things, like to bring those patterns to your code. So in this case, you've got cashier and barista as two services. And a message comes in, the order message or the order drink comes in. So here, what the cashier does is the cashier charges your card, processes that message. When that message occurs, the main object or the goal for the cashier is to charge money. So that operation happens. Once that operation happens, a message is published. So drink is ordered. So think about this message as that cup that got queued for the barista. Now, the barista is listening or subscribed to this event. So the barista gets this message. And the barista then processes this message and publishes an event, the drink prepared event. So in this model, you have you as the consumer get this event because you're subscribed to the drink prepared event, and life is good. So there is no crazy polling or, so the cashier, the barista is not asking the cashier, hey, do you got any, orders for me to fulfill? There is no polling. And everything organically happens as events, as and when they occur. So it's a more natural, real world based. Now, the beauty of this is because these are entirely, if you look at this, they're autonomous. The barista service could go down. You can think about Starbucks where shift changes occur and one barista changes out for the next barista, right? During that time, the cashier does not stop to, the entire Starbucks thing isn't stopped. The cashier still continues to get the money and helps clear the consumer line. And meanwhile, every order they're processing, they're leaving a message in the queue for the barista. And it doesn't matter, the barista comes back, a second later or a minute later, those messages aren't lost, those drink orders aren't lost, they're there. And the barista, once they come, they can process the message and everything is good. So now what happens if the cashier is down? The cashier might just have gone to go and grab a croissant for someone. It doesn't matter. The barista can still continue processing what the barista is supposed to do. So you have these, you have the reliability baked in with this event-driven architecture and with the messaging. So event-driven architecture is really a style of architecture which enables your applications to model the real world by publishing events or sending messages as and when things occur, as opposed to this whole command or command control style of architecture. Now, you need something that takes these messages from one place to the other. And that's where the sort of bus or transport comes in. So you need to have a transport. So there are several different transports. In Microsoft, you've got the built-in, baked-in MSMQ that comes out of the box. It's still alive. And then you have the cloud offering. We've got Azure Service Bus. You've got Azure Storage Queues. If you're in the Amazon side, you've got the Amazon SQS. So all these, of course, RabbitMQ, the kid on the block, right? So you've got all these different transports that give you the ability to send messages across. So where do these messages go? They have to end up in a queue. That's where a queue, you can think about the queue as a place where messages need to persist. So the bus comes, drives the message, and the message gets delivered. It's like a little persistent store where it's going to be there until like the process, whichever process that was supposed to process that message has a chance to process that message. So it's just a store. If you're climbing Mount Everest, queues is a bad thing. Queues is probably a bad thing in real life. But for software, queues really work well. It helps to decouple things and get rid of temporal coupling. So event-driven architecture is fabulous. It's great. You should use it. Yes. But this may be your reality today where you're dealing with monoliths. And so if you're dealing with monoliths, you already have something in place, and you're thinking about like how I got to deal with this, and I have to build features, new requirements. I have to be able to work with this. So how can event-driven architecture help you here? I kind of want to share some of my experience here. So we had this system. This was before I joined particular software and Service Bus, and I used to work for this company. And so we had this big, giant, big monolith, which was there 5 or 6 or 7 years before I got in. So we had this big process. And so when a customer file got dropped, we've all dealt with CSV files in the past. So we had to process each line, and each line translated into a series of steps and customizations that needed to occur. And at the end of all that, something got shipped. Now, there was a problem where we had a customer and we had an SLA, and somehow their files were taking too long. And we noticed this more because they were our large volume customer who dropped more files. So we wanted to kind of see like, what is taking so long, and how can we, where can we find this flaw? So, and we had no visibility. We had this massive service that everybody was afraid to touch, because if it works, you better leave it alone, especially if it's a legacy code. And so it's like, but it isn't working. You're trying to figure out what's causing the time. So what we were able to do there is we were able to go and make small changes where we were able to go and instrument this monolith with events. So we went to each part of the code that was doing something. We were able to identify like which, something when something of significance was happening to the business. Some step A completed, step B completed, right? We were able to go to these points, and we were able to publish an event. And then we added a subscriber that was listening to all these events. So we kind of had an idea of like, okay, A got done, B got done, C got done. So finally, we had eyes into this thing. We were able to see what was taking long. So it turned out that the part that was taking long was this one step. And then we were able to drill into that step, and we found out that that step was making a RPC call to the service that did some calculation. Yes, the service was actually running in the same infrastructure, so it wasn't like a service that was running like long or far away. But it was doing some calculation. It was taking some time, but the time it took, like it added up for every single line in the CSV file. It was like a compounding effect. And then when we dug a little bit more, it turned out that no one was actually using that. So it was calling the calculation. It was, finding out that value. And it was writing in this very important table in this database, and the table of 200 fields. But it wasn't being used. So we got lucky, I guess. So we went and commented that one line of code, which was making this RPC call, and we were able to get like a 30% immediate performance jump. So everybody was happy. But that kind of stuff would not have happened if we didn't have visibility into the system. So this is kind of what we did. So we went to the monolith. So if you want to want to try something like this, it's a minimally invasive change to your monolith. So you're not changing like how it works. So it's not going to like break everything down. But it's a minimally invasive change. You go into the domain, and then you go into the code and figure out like where important stuff is happening, and then you make it emit an event. But what this allows you now is it allows you to build things on the outside. You could have, like, because now these things are event-based, when a company comes and tells you, when this, let's say, client became preferred, so whenever we mark someone as preferred client, we want to send them some new promotion. And that's something, let's say they just want to try out and see whether it works or not. You don't have to now go into that big giant monolith to build this function. Because you have this monolith emitting out events, you can build this small service that does just promotions, and you build it on the outside. It doesn't even have to talk to that same database with so many tables and so many fields. You could, it doesn't even have to be a relational database. It could be whatever. It could be a flat file. It could be whatever you need it to be. It could work with the persistence of what it needs to do its job, which is customer promotions. So you can build this thing completely on the outside. So it gives you this flexibility. So even with monoliths, you can use event-driven architecture to kind of break things apart and give you this flexibility. And Martin Fowler talks about this pattern called strangler pattern. So where he talks about this, pattern where you slowly carve out parts of the system into its own thing, and eventually this monolith starts losing its meaning. So you could use events to try to gradually get the data out of what you need out into your own new system, where you feed it to your systems, which is very, very specific to what you're doing, doesn't have to deal with the one view of customer, which has 20,000 things that you don't need for customer promotions. You use your DDD principles and just take what you need for that representation of customer that you need for customer promotions. So this customer promotions is just a consumer of an event. So now if we talk about some of the gotchas or nuances you need to think about when you're dealing with messages, one of the things that you need to be aware of is in messaging, your messages can arrive out of order. You could send them in whatever order you want, but on the receiving side, you cannot guarantee the order in which those messages are received. So let's say you've got two messages, a cancel order or a submit order, and you have a simple service that, when the submit order message comes in, you take that order and you write it to your database. And when the cancel order comes in, it's simple. You check if there's an order already existing in your database, and if it's not no, then you go ahead and call cancel order. Well, let's look at these two things together. You've got submit order, you've got cancel order. Now let's switch up the order, right? What if you did not get submit order first? What if the cancel order came in first? well, buyers have remorse. As soon as you buy something on Amazon, like, oh, nope, don't want it, right? So that can happen, and that could have happened when the customer had canceled the order. So what if they came out of order? Now here, according to this code, for very good programmers, we always are taught to check for null, right? So we check for null. In this case, there is nothing in the system yet because we haven't seen the submit order message. So the message for cancel comes in first. There is nothing in the system, so the order is null. So this just happily says, OK, I've got nothing to do. But the message has been processed. Now you get the submit order. And now you write the, hey, there's a new order in your system. But the customer had actually canceled the order, but your system has no knowledge of that. It's completely lost that thing that the customer actually canceled it. And you go through the fulfillment process of sending that item, charging that card, and the customer is calling you very angrily, like, hey, I canceled this order right after I placed it, right? So you could run into those type of problems with messaging, and you need to be aware of that. So one of the patterns that can be used is the saga pattern. It's essentially a pattern which lets you work with multiple messages at once. It's very good for orchestration or business processes, implementing business processes. It's a message pattern which deals with messages, and it has a state. Usually, processes and orchestration have some kind of state attached to it. So we call this the saga pattern, and it usually deals with a state object. In this case, it's an order data. It could be anything. It could be just a class. So in this class, you kind of like put in all the state information. So let's say the cancel order comes in. You say that, I've got this message, and you remember that state. So when the submit order comes in, you know that, hey, this has already been canceled, so I don't have to save this information in the database. So you could take a lot of compensating actions. Like Expedia has this process where you can cancel your ticket within 24 hours and you won't be charged. So you don't even have to start processing your orders. You just simply wait for 24 hours and then see what happens. If within those 24 hours, if you've got a cancel message, then you haven't kickstarted your ordering at all. But 24 hours elapsed. Now you get the, then you can go ahead and publish an event saying like, hey, this order is good to go, and then you can start fulfilling the process. So this pattern is useful in that. Now, I want to kind of share some of my experiences with the messages when, when you're dealing with messages, what kind of messages, because you have everything talking to each other in terms of messages. You publish an event, you subscribe to an event. So what is this event or a message? It's just, you can think of it as a DTO. It's a piece of information that needs to get shoveled from one place to the other. So we said that this whole land of event-driven architecture, the style of programming and architecture and messaging helps you reduce coupling. But you could, what I learned is that you could still introduce some coupling in terms of like how you come up with the schema for these messages. Because for something to understand the message or push the message, both the sender and receiver need to understand the schema. So they need to share the schema. The sender and the receiver need to understand the schema. So your message schema, therefore, becomes important. So what you put in that message becomes important. So if you have like large amount of data, and then you start changing the fields and stuff in that DTO, in that message object, you got to worry about downstream, how is that going to affect the subscriber? If you just removed something from the schema that a subscriber is one that the subscriber is reliant on, then you've broken something. So you could still have that coupling using messages and That's why you need to be important of how you define the schema. So typically, just like in a DDD world, you've got different views of the same object. You've got the customer in one system, you've got a customer in another system, but the ID is probably the same because you're talking about the same customer. So you don't have to shovel a lot of data, just have the customer ID. And the thing that happened, you express it in terms of domain language. What programmers, sometimes when we come up with these message names, we come up with PDF document generated, right? But that has no meaning like for a domain person. Like, what PDF document got generated? But if you meant that as order shipped or mailed or something in the domain language that everybody can understand, your events are more meaningful. The messages that you send are more meaningful. So you have to put some thought into how you're naming these things. Yes, naming things is one of the hardest things, I guess, in computer science, but it's still an important thing to do, right? So that's super important. One of the other things that I wanted to talk about in messaging is this ability to be idempotent. What is idempotency? Essentially, let's say you have some piece of code, some message comes in, you handle it. Now that piece of code, can the same message come in like 3 or 4 times or whatever times? If you pass that same message to your handler code, will there be any side effects in your overall system? Some operations are inherently idempotent. Let's say you're trying to update like an address change, right? No matter how many times you pass that message saying the new address is going to be blah 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 street in Murrieta, right? You can call the handler 5 times, 10 times, doesn't matter. The same information is going to be written in the database. So that operation is inherently idempotent. But what about charging cards for a customer? Like once you've processed the card, that's it. I mean, you don't want to reprocess the same message 5 times and have angry customers calling you. So that operation isn't idempotent. So you need to be able to identify what operations are and aren't, and you need to design for it up front. Now, this is where you have to pay attention to what kind of transports you're using for the messaging, because different transports support different capabilities. MSMQ, the old and darling child, supports distributed transactions. So it guarantees the once and only delivery of a message. But transports like Rabbit don't support distributed transactions. So in case you're using a transport like Rabbit, you have to keep in mind that it is possible to receive duplicate messages. So how is your system going to be able to handle these duplicate messages? There are messaging patterns like the outbox pattern that can help you deal with it. So essentially, the outbox pattern is where a message comes in, you process that message, and now you put that information in some kind of like persistence saying, oh, OK, I've seen this message was processed. And you kind of hold on to that information. The next time a message comes in, you kind of check your process messages first to see if you have seen this message already. If you've seen it, then you just simply discard it. Now, it sounds kind of simple, but the devil is always in the details and trying to work with these transactions and how you coordinate them. So if anybody's interested, come find me in the blue space area, I guess, and we can talk more, or I can point you to a 15 or 16-minute video that talks about all the things you need to take in mind to implement this outbox pattern in order for you to be able to successfully dedupe and not have duplicate messages revolving around. Because it's important, because we said that when an event gets published, lots of other systems or contexts go off of that event. When an event is published, events are things that have happened in the past. You could state with authority that this has happened. So all your other systems rely on this information and go take actions based on this information. Now, if your handler, because of a duplicate message, publishes an event, but and there was a rollback in your handler because Rabbit doesn't support distributed transactions, it's already sent out the message, it's already published that event, but you have now some inconsistent data in your database. You don't have the order, but you've just went ahead and published this event. So you could kind of end up in this inconsistent state if you don't account for duplicate messages in your system. So you've built this system, and you've got messaging going on. And you've got to worry about, when you're debugging these systems, where is your message? It's kind of hard, because now all of a sudden, there's not just the one database that you go and check all the time. It could be messages that are in transit. They could be waiting in a queue for one endpoint or another endpoint. So now you're kind of trying to track, where did my message go? And this is where auditing comes in. This is where message auditing comes in. If you can take a copy of successfully processed messages, forward it to a queue, and maybe you can store that information in a database. So now you have a log of all the messages that were successfully processed. So from there, you can kind of see what message really happened, what didn't, and you can debug. At particular, we kind of built our whole message visualization tools based on just message auditing. We were able to audit them. From the audit messages, we were able to extract metadata from the headers, and we were able to build this visualization tool that kind of shows the whole entire message flow just based on the headers and the audit information. Now, this is particularly useful when you have business processes and sagas, because it kind of gives you the whole visualization at one point, rather than you having, if you didn't have this visualization, you'd have to hunt the logs and then try to build this state object for your business process, what state was it when this message got sent out. So you have a lot of debugging to do if you don't have the supporting tools for messaging. So in this kind of manner, when you're building systems like this, deployment becomes a lot simpler. It's not throw it all and then bring it all down and then schedule some time. You might still have to schedule time for deployment. It could be your business process, but it's not bring the whole entire system down, update it, and bring it all back and then see it work. You could have side-by-side deployments. Because these are small autonomous components, you've got, you're successfully running 1.0 code, which is processing messages. You could simply introduce a 1.1 version of the code and just watch. And some messages could go to your 1.0 code. Some messages could go to your 1.1 or your new version. Once you've ascertained that the messages are getting processed properly, then you could stop your V1 and roll with V next. Now, what happens if, this is the happy-go scenario where everything works great. But as we all know, people who've deployed code in production, things are not always rosy. You deploy something and something breaks and you have to do a rollback. And so you deploy 1.1, and when a message gets processed, you figure out this did not go so well, and there was an exception that could not be successful after retries. Like a null reference, if your code throws a null reference exception, it doesn't matter how many times you retry that message, it's going to always fail. So in that case, it gets pushed to this error queue. So it isn't lost, it's pushed to a different queue, and it's kind of waiting there. So now ops guys can stop this offending piece of code and go yell at developers saying like, hey, it's not working. So then the beauty of this is you can take the message that is sitting in the error queue and just successfully process it because your 1.0 is still running. You simply take the message from the error queue, throw it in the queue for your endpoint, and then it processes its message. So you have this ability to run even when things fail. And of course, you fix your issues, and things get happy. So there are two things I want you to take away from this talk. One is, reduce temporal coupling and naturally strive for autonomy. When you're thinking about these services and contexts, think about, can they operate independently without being dependent on other services? And always, when possible, use messaging to achieve this asynchrony. So this ebook, if you want to learn more about the fallacies of distributed computing, you could go to that link and download the ebook. It goes about the different fallacies, not just the network is reliable or latency is 0. There's several more of the fallacies that you need to be aware of, so you could have a read. So when you walk out of this door, I want you to do two things. One, I want you to think about this. What happens if you go and randomly, please do this in your staging or testing environment. What happens if you randomly start killing some processes, and then start them back up? Are they, how is the state of the system? Are they able to resume successfully if the failures and things happened? Or even more drastic, go and bring down your database just for 2 minutes, and the all-important database, and then see how your systems react. And yeah, that's what I want you to think of and think how you'll solve for autonomy and asynchrony. Thank you.